Hi everyone. In this video, we're going to go through section 1.6, applications of linear systems. So this is the first time in the course where we get a look at how linear algebra is and can be used in various fields. We get it broken down into three different types of examples in three different areas of our work systems, and we'll get to those shortly. But one thing that I would suggest doing, the beginning of all the chapters give a lot of the applications and the historical context to how linear algebra is used. I highly recommend reading that. So at the beginning of chapter 1, the text talks about a Harvard professor, Vasily Leontief. I'm not sure if I said his name correctly, but in 1949, he fed punch cards into a Mark II computer that his university had, and the cards contained information with like more than 250,000 pieces of information that the U.S. Bureau of Labor and Statistics had collected over a couple of years of work. He divided the economy, the U.S. economy, into 500 different sectors: coal, automotive, communications, etc. So 500 different sectors, and for each sector he had a linear equation that described how the sector distributed its output to the other sectors. So how the automotive industry distributed its automobiles, its output, to other sectors, because like the oil industry would need various automobiles, et cetera, et cetera. So he had a system of 500 equations in 500 variables. That's pretty intense. Imagine solving that by hand. And he had to, because computers were not good enough in 1949. He had to reduce his system of 500 equations and 500 variables down to 42 equations and 42 variables, which must have been an insane amount of computation. He used linear algebra to do that. And then once it was 42, he was able to use his computer, the computer at his university, to solve that system of equations. So the stuff that we do has been used throughout history. Now we use computers extensively, but part of the goal of this course is to not only understand the computation and how it works, but to understand the theory of why it works and why we're able to program computers that can now solve even larger than systems of 500 equations and 500 variables. So give that a read. I kind of read through a lot of it, but it's understanding connections to the real world is a part is an important part of getting out all that you can out of this course. There's my little intro for you today. All right. So we are going to start with that economics application, and we have our nation divided into many different sectors, and we're going to use the word price here in this first example that we'll see shortly. But what that price represents is the total dollar value of the sector's output. The total dollar value of the sector's output is called the price of that output. Okay, so what Leontief proved is that there exists equilibrium prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances its expenses, so that we're finding an equilibrium for our system, our economy. So let's take a look at and go over the visual of this first example. All right, so we have the prices of the total annual inputs for coal, electric, and steel is denoted by P subscript C, P sub E, and P sub S, coal, electric, steel. If possible, find the equilibrium price that make each sector's income match its expenditures. Okay, so the way that we lay out this information is we have coal, the distribution of output from coal purchased by coal is apparently 0. Coal does not purchase any of its own coal. But in our little system, our little economy, 60% of the distribution of coal is purchased by electric, 40% of the distribution of coal is purchased by steel. Okay. For the electric industry, 40% of what the electric industry produces is purchased by coal. 10% of the electric that's produced is purchased by electric, so 10% goes into running and maintaining the electric industry itself. and 50% of the electric produced is purchased by steel. And then we have the same breakdown for steel. On the right here is a more visual intuition of how these three systems work together. Now, the first step in like analyzing this problem, once we've looked at all that kind of general overview, what we're going to start with is kind of identifying what each industry is purchasing. Okay, so we're gonna write down an equation for what the coal industry is purchasing, the price of coal. We're going to write an equation for what the electric industry is purchasing, the price of, that's an E, electric. And we're going to write down an equation for the price of steel, what the steel industry is purchasing. Okay, so for coal, they're getting 40% of the electric, 60% of the steel. So that's 0.4 times the price of electric plus 0.6 times the price of steel. For the electric industry, I'll change colors here for my underlining. They're getting stuff from every industry. So for electric, they're getting 60% of the coal that is produced, 10% of the price of electric, the electric that is produced, and 20% of the steel that is produced, the price of steel. All right, and then the last equation, the steel industry, 40% times the price of coal plus 50% times the price of electric plus 20% times the price of, oops, that should be an S, times the price of steel. So we're looking, that's terrible, we're looking horizontally at this table to set up our three equations. All right, so the next step is, now that we have all of how these different sectors of the economy work together, right, we're going to set up a nice looking system of equations. And since we have variable terms all over the place, we can write a system of equations that is homogeneous, that is, each equation is equal to 0. So moving everything, let's see, to the left-hand side on my first equation gives me P sub C minus 0.4 P sub E minus 0.6 P sub S. The next equation, negative 0.6 P sub C. Let's see, plus 0.9 P E minus 0.2 times the price, 0.2, of steel. And negative 0.4 PC minus 0.5 P sub E and plus 0.8 P sub S. Okay, so that's what you get when you bring everything over to the left-hand side of the equation. And now, gloriously, we can just set up and solve and row reduce an augmented matrix. Okay, I am going to jump right to the reduced matrix. If you're using your TI-89s by this point to put it into reduced row echelon form, that's great. I highly encourage that. And what I end up with, so I'm taking this system, writing an augmented matrix, type it in my calculator, put it into reduced row echelon form. It looks like this. 1, 0, negative 0.940, 0, 1, negative 0.850, and then a row of zeros. Okay, so let's kind of analyze our results here. We're not done with the problem. We got a little bit more to go. Okay, so the first thing, since we have a homogeneous system, right, that guarantees that we do have a solution, right? We do have a solution that is the trivial solution. They can set all their prices, coal, electric, and steel, to be 0, and hey, we have a balanced economy, but we're not doing much. That sounds like a terrible idea. All right. Here, in our reduced matrix, because we have a row of zeros, we lost a pivot. We have more than just the trivial solution. We have infinitely many solutions. So let's write what that solution looks like. Okay, so we're going to go, our price is equal to the price of coal, price of electric, price of steel. And using the techniques from the previous section, we have our free variable is the price of steel. So we write all three, 0.94, that becomes positive 0.85 times, write all three solutions in terms of that one free variable, like that, and then factor that free variable out of our vector, 0.94, 0.85, and 1. So what does it all mean? Let's say we set our price of steel to be our free variable to be $100 million, right? That tells me that P sub C, the price of coal, is $94 million. The price of electric is $85 million. And remember, the price is not the right context here. That's the total output of each of those three industries. If they're $100 million, $85 million, and $94 million, then our system, our industries are in balance, in equilibrium. All right, our next application to linear equations is we can use matrices to help us balance chemical equations. Okay, so take a look at this. I don't know if there's any chemists in the class, but what do we have? What is our chemical equation here? I believe that we are burning propane gas, and that propane combines with oxygen and produces carbon dioxide and water as a result of that. Okay. But what we don't know is how many elements, or how many atoms of propane, oxygen, carbon dioxide, and water make this chemical equation balanced. Okay, and what we do, the approach here, is to write each of these atoms with as a vector. Really, the top entry in each vector represents how many atoms of carbon are in each compound. The middle entry is how many atoms of hydrogen. The bottom entry, how many atoms of oxygen in each compound. So I want to write the above chemical equation a little bit differently, more algebraically, right? So what I'm going to do is I'm going to say, all right, x1 times this first compound plus x2 times this second compound here. And it's not going to be plus and plus, it's going to be equals, because the right-hand side of the equation is equal to the left-hand side. x3 times that compound plus x4 times that times the last compound, 0, 2, and 1. So when I write my augmented matrix, these two guys are going to have all negative signs. We're going to bring them to the left-hand side in order to represent this system of equations as an augmented matrix. So I'll write down what that looks like and then jump right to my reduced echelon form, right? 3, 8, 0 for my first vector, 0, 0, that's a 0, 0, 2, minus 1, 0, minus 2, 0, negative 2, and negative 1, okay? And I could put a row of zeros because this is, again, a homogeneous system. So we have the zero vector, again, that balances the equation. Not very interesting. If you jump right to your reduced echelon form, actually, I'm not going to write it. Well, I will. Yeah, I'll write the reduced echelon form, and it looks like this. Let's see, 1, 0, 0 for the first column, 0, 1, 0 for the second column. My third column is 0, 0, 1. And then my fourth column, this is the one that has some interesting stuff in it. Negative a quarter. Let's see, negative 5 quarters. And negative 3 quarters. And then 4 zeros, or 3 zeros. There we go. So that's my reduced echelon form. And what does that mean? It means that x4 is free, x1 is 1/4 x4, x2 is 5 quarters times x4, x3, there we go, is 3 quarters times x4, and as I said already, x4 is free. Okay, so to come up now finally with the solution for this system, okay, so to balance our chemical equation, we're going to choose a good number for x4. Let me come up here. I'm going to say let x4 equal 4. Why am I picking 4? Because then when I substitute x3 is 3/4 times 4, which is 3. X2 is 5/4 times 4, and x1 is 1/4 times 4. And so these are the numbers that balance this system at the top. I need one of these. I need that was the propane, I think. Let's see how many oxygens. 5 of those, 5 oxygens, and then the system produces 3 carbon dioxide compounds and 4 bits of water. There we go. Okay, so there's the second place where linear algebra can help us to do to solve for some unknowns. And now the third application that we see in section 1.6 deals with what's called network flow. And so we'll look at the example in just a minute. It says determine the general flow pattern for the network. And these are a series of intersections in Baltimore streets. But the first thing that you need to know is that our network is made up of what are called junctions or nodes. N-O-D-E, nodes. And the way that a junction or a node works is that if I have, that's a little arrow on the line, if I have a value of 30 entering a specific node, then I have to have a value of 30 exiting that node. So in that case, with that like little node, I would be able to write down the equation x1 plus x2 is equal to 30. Okay, that's like important preliminary information for you to understand in order to address the problem that we're going to look at here. Okay, so now getting at this question, so we have 4 different nodes within the four different nodes within this network. They're labeled A, B, C, and D, and we need to look at the inflow into each node. So for example, into intersection B, we have an x4 and an x2 flowing into intersection B, and flowing out, we have an x3 and a 300. So on Calvert Street at intersection B, we would be able to write down, we can write down an equation to model that flow, right? We have x2 plus x4 going in, and x3 plus 300 flowing out, and we can write down that equation. And let's do that. So let me move it up a little bit. I'm not sure why I'm starting with B, but I am. So we'll go back to A in just a second. Okay, so for intersection B, x2 plus x4 is equal to x3 plus 300. Okay, now you can pause the video if you want and do the same thing for the other 4 intersections. But for intersection A, we have values of 500 and 300 flowing in, so that would be 800, is equal to, then we have values of x2 and x1 flowing out of intersection A. Okay, the same thing for C. What do we have flowing into C? We have 100 plus, 400 flowing into intersection C. So I could have just written down 500, but that's okay. And then flowing out of C, we have x4 and x5. All right, and then last, intersection D, we have, x5 is flowing in, x1 is flowing in, x1 plus x5 is equal to the only outflow from intersection D, or that node, is 600. Now we can actually write down one more equation that doesn't deal with any of the nodes, but deals with the network as a whole, and that is that the total flow into the network is equal to the total flow out of the network. So let me just highlight all of that. There is all of our flow in and out. Okay, so let's get an equation from that. Let's go with in first. All right, and this is I'll put it above the intersection A. So flowing in, starting at the top, I have 100 plus 400 plus 500 plus 300 is equal to, flowing out again, starting at the top, x3 plus 600 plus 300. So we have 5 equations, and let's see how many different unknowns. 5 unknowns, but that top black equation that I have written down there, right, that tells me one of my unknowns already. So our next step is to take these 5 equations, right, we'll write them in a way that looks more familiar. So I'm going to draw a little arrow over here. The top equation simplifies to x3 is equal to, let's see, what does it end up as? 400, I think. Yes, 400. X3 is equal to 400. The A equation, x1 plus x2 is equal to 800. I don't like where my x3 is lining up, so I'm going to change that. Put it right there. That's better. All right. The B equation, x2 plus, or x2 minus x3 plus x4 is equal to 300. C equation, that's going to be x4 and x5 is equal to 500, and then x1 plus x5 is equal to 600. Good deal. All right, so then we can do our augmented matrix, right? The top equation, 0, 0, 1, 0, 0, 400, and then 1, 1, 0, 0, 0, 800, 0, 1, negative 1, 1, 0, 300, 0, 0, 0, 1, 1, 500, 1, couple of zeros, 1, 600. So now we have our augmented matrix, which we can put in reduced row echelon form and come up with a solution, right? And the solution is the general flow pattern for the network. So I am going to jump right to what that solution looks like. Hopefully by now you're getting a little bit more used to, like I said, using your TI-89s to get it into reduced echelon form. But let's represent this solution. x1 is equal to 600 minus x5, x2, 200 plus x5. So you can see that we have a free variable here, right? x3, we already knew that was 400. x4, 500 minus x5, and x5 is our free variable. Okay, so that we can choose any value of x5. Well, not quite any value of x5, right? Because I have to be careful. If I pick an x5 that's too large, I would have a negative traffic flow. So that would be kind of strange. So we're technically limited here. Let me use a different color. We're limited here in that x5 has to be less than or equal to 500. We don't want that x4 value to be negative. That's the only real constraint here. Okay, and right, so that would be, this is our general flow pattern for this network, this system of streets and intersections. Cool. So that concludes this section. You are now hopefully prepared to work on the homework problems. They're kind of examples of each type of question that we encountered in this lecture. And if you have any questions, if there's something that wasn't clear, something you're unsure of, please let me know. Thank you for listening, and I hope you have a great day.